So a little bit about me, for those who don't know me. My name is Donna Wrublewski. I am the chemistry and chemical engineering librarian up at Caltech in Pasadena. So what the heck am I doing at an R user group meetup? Back in about, I think it was 2016, there was an interest in the carpentry movement. So you may have heard of data carpentry, software carpentry. It's a nonprofit group that promotes 2 or 3 day, sort of like bootstrap workshops to like get people, and particularly researchers, up to date, or at least immersed and familiar with working with either Python or R, in an attempt to get them, working with and analyzing their data as quickly as possible, without having to take, a computer science class. So this movement caught on kind of like wildfire on our campus. So a whole bunch of us in the library got trained. There's a number of us actually that do have hard science backgrounds. So some of us got trained. So like I have a PhD in polymer science. My colleague had one of my other colleagues has a master's in geology. There's another one of our employees is working on their PhD in computational chemistry. So a bunch of us all decided, let's get trained as instructors because we wanted to start offering these workshops. So I had used MATLAB and Scilab a bit when I was working on my dissertation, and R, and I played around with R a little bit, but not very much. So this was a really good excuse to kind of get back in with that. So the talk that so I've done a number of workshops focused on R and data analysis. And so today I'm going to talk a bit about designing a workshop for chemists, basically, and people interested in what can you do with R in terms of reproducible analysis and data with chemistry. So data carpentry workshops, software carpentry workshops, or the carpentries as they're now known. And, probably most of the classes that you may have taken, these are things that, may span a couple of days, potentially a week. Caltech offers 2 classes that are both like week-long boot camps in this. So our goal was to see, maybe what can we do if we had like 5 hours, right? So the idea was that, and actually I should immediately, there we go. I will introduce my co-authors right now. And this was actually their idea. I got kind of brought on this a little bit late. We'd been talking for a little while. My colleague Ye Li was the chemistry librarian at the University of Michigan for several years before moving to Colorado, and then she moved to MIT last year. She became acquainted with Steve Wathen, who's a professor of chemistry at Siena Heights, which is also in Michigan. And Siena Heights it's a small, mainly undergraduate institution. And I think Steve got in touch with Ye about library resources. But it turns out that Steve actually teaches in one of his undergraduate chemistry lectures, one of his lab courses, he has them do a lab on data analysis using R. And Ye and I have been talking for a while that it would be really cool to do a workshop at the American Chemical Society meeting. There's like 10 to 15,000 people there. It is kind of an expensive conference. So can we do something maybe, subsidized? Can we, how long should it be? People will need to travel. So after much planning for the better part of a year, we decided, okay, the fall meeting last year, the American Chemical Society meeting last fall was going to be in San Diego. The meetings usually run Sunday to Thursday. Let's run an experiment and do a 5-hour workshop the Saturday before, see how many people we get, and just see how it goes. So let's see. All right, so this actually was supposed to be a poster at the Chemical Society meeting that just got canceled in Philadelphia. But this basically is just the summary of the poster that we were going to give and the report that we were going to write for our funders. Where basically the idea is, can we construct sort of like a 5-hour R workshop? And the assumption is that the people walking in would have no experience whatsoever with it before. And we wanted to give a demonstration of the entire, I would say data analysis, or kind of, workshop experience where we take people, they don't have any experience with R, we'll give them some background. Okay. So the very basics, get them started, get them familiar with R, have them do actual work. So actually run through a lab experiment, do some actual analysis, data analysis like they would do in the lab. And then finally, the part that we added on that carpentry doesn't really talk about is have them create some sort of reproducible report in the form of an R Markdown document. My colleague, Gail Clement at Caltech, has been pioneering the author carpentry movement. So to kind of complement data carpentry and software carpentry, author carpentry is how do you reproducibly, say, like write reports, do, create your own profiles, do bibliographies, things like that, in a reproducible way, and keep it all within that framework. So that was going to be the third part that we were going to tack onto it. So what I'll talk about, for the next however many minutes is sort of what are the logistics of doing this. And then we will actually look at some R code, I promise. I know that that's mandatory for these things. But again, as an educator, I'm always, I always like, tooling around in R and doing neat things. But to me, really, there's a lot of, the fun part for me is, can I turn this into a lesson to help somebody solve a problem? I'm a teacher, I've been a teacher, and this is just kind of, I'm really interested in this. And I think there's so many resources out there that you can teach yourself with, but sometimes some people just learn better just sitting down and talking with somebody and hashing out a problem. Or a lot of people learn better by, following along an actual person, that's doing an example. They can stop and ask questions if they get stuck, things like that. Okay, so that's kind of like the background behind this. Just some of the goals in our audience, again, as I said before, the idea is to kind of expose people who may not have experience, have been experienced or exposed to this, the idea of using script-based data analysis, that's the big power behind R and Python and tools like that, and authoring tools, so that, chemists can kind of see how can they streamline their data workflows, how can they enhance reproducibility. And in her introduction at the workshop, Ye talked about, the whole reproducibility crisis and things like that, and how tools like that can solve that. In terms of improving the transparency and reproducibility of the research processes. So we wanted to give folks who came like a hands-on learning experience so they could kind of firsthand see what this would be like, and also have people, again, we had a mix of graduate students, librarians, computational chemistry professionals, a whole bunch of folks, basically give them resources in the form of slides or our open GitHub repo. I've got the link coming up. So the resources that they can take back and share with their communities and say, hey, this is something cool. So even if it's something they may not directly apply in their day-to-day life, but something where they can say, for example, hey, have you heard about this? This could be something cool. Maybe if you're a librarian, for example, take it back and, talk to your chemistry, faculty about this and say, hey, have you guys heard about this? So yeah, so our intended audience was, I'm a member of the chemical information division. So we're primarily like informaticians, librarians, people who work with the information as opposed to doing actual bench chemistry and analysis. But, so we were, kind of reaching out to our own folks, but we did advertise it pretty broadly. So we had a mix of students and librarians and people who actually do like informatics professionally. So a little bit about our logistics. So we did this on the Saturday before the meeting. We started at 9 a.m. We ran till about 2 p.m. And we had 2 short breaks and a longer break for lunch. Some of the feedback we got was that this should have gone longer. We would have loved to go longer, but there was a divisional executive committee meeting that started at 3, so we had to wrap it up a little bit earlier. And we did this at the Omni Hotel in San Diego, which was pretty close to the convention center and an ACS hotel. So, people coming into town for the conference, they wouldn't have to be, changing hotels or running around a lot. We wound up having 21 people register, 18 actually paid and attended. And in terms of payment, the instructors, we all donated our time. We didn't take a dime for this. And we charged each of the participants a $40 registration fee. largely to ensure attendance, because a lot of us have found that when we do events at our home institutions that, you know, if we don't have some sort of, you know, at least token payment, attendance can be very, very low. And we also did get sponsorship from ACS Publications. So the division of ACS that publishes all their journals, they really like us. So they sponsored the rest of our facilities fees. And my division, Chemical Information Division, helped with logistical support and some contingency funding. So if you've been, if you're familiar with the Carpentries design, we generally that's run, you have multiple instructors. So in this case, we had 3 of us. At any particular time, one person is teaching, the other 2 are kind of going around the room acting as basically teaching assistants. And we have a system using sticky notes. So we have 2 different color sticky notes. I guess in this case, we use red and blue. Sometimes we use yellow and blue, red, green, trying to account, you know, make sure that we don't aggravate anybody's color blindness. So in this case, we're using red and blue. And so generally, if during the course of the class, you know, we'll give an exercise and say, okay, everybody go do this, you know, run this bit of code. And see what you get. Put up a blue sticky note if it worked, put up a red sticky note if it didn't. And generally during the class, if at any time during the lecture, if people have a question, they can put up a red sticky note and one of the 2 non-lecturing instructors will come over and help them out. So this is good because it kind of, it does keep the class moving, but it does give the opportunity for folks, you know, if they do get stuck or have a problem to get help to kind of catch up. So that's a layout of the room there that we had on the left. It was mostly, I think it mostly went okay. I mean, there was enough room. There were a couple of things that could have been better. I'll talk about those later. But that was generally the setup there. And that's my colleague Ye teaching. And then over on the right, usually, and at the breaks, what we do is we have the students, we have the learners in the class put something that's working well for them on one color sticky and then something that's not working well that needs to be improved on the other. So like, for example, I think in this case, we had a bunch of people asking, you know, hey, why is it so cold in here? You know, can we change the temperature? Or can you go a little bit faster? Can you go a little bit slower? Things like that. So it's a way to get real-time feedback. So I think we did 1 round of those in the morning and then another round of those after lunch. So that worked out pretty well. So we can make adjustments to our class, like sort of in real time while we're doing it. And then we usually keep those afterwards and look at them. So it's a great system. We love it. I try to like sticky eyes everything. So the content that we did was we basically broke it down into 3 parts. We had an intro to R and R Studio, which is taught by Ye. Working with QSAR data, taught by Steve. So that's quantitative structure activity relationship data. I'll talk a little bit more about that. Like there's like I have a 1-sentence definition of that later. And then finally, the last part was creating a reproducible report using R Markdown, which is a section that I covered. So we used, we thought about how to set this up, and we thought, we thought about what the best way to do this was. And you know, there were 2 options. So one was we tell everybody, okay, you got to install all this stuff on your computer and then come. And now we've had problems with this where people might have the wrong version or they don't have the right administrative privileges to add stuff onto their computers. So what we decided to do was we got in touch with RStudio and we said, can we use RStudio Cloud? So we created a virtual environment that had all of the pack. Actually, we didn't even use anything beyond base R now that I'm thinking about it. So we had, I'm sorry, somebody else in my apartment is on the phone. So we set up an RStudio interface and we loaded all of the files that they would need in there into that interface so that all that they needed to do was just log in once they got there. So really, we just needed to provide a good internet connection. And that actually worked really, really well. So there was basically everybody got in, logged into their machines, got on the internet, logged into RStudio Cloud, ready to go. So that worked out really well. Okay, so do we want to have a look at the lesson? Let's go. I know in the LAE Star user group, there's a whole thing about you have to have a GIF in your presentation. So here's my token GIF. Okay, so I'm going to get out of here. And I believe I'm still screen sharing. So you should be able to see my RStudio window here. So what I'm showing you now, this is the master repository of all of the materials. So the student interface that people saw on RStudio Cloud looked a little bit different. It didn't have some of the slides, and it obviously didn't have all the completed exercises. So they had kind of a little, like a pared down version of this. But we talked a little bit about, you know, the importance of setting up an R project file and working within our project. And then setting up different folders for, you know, your data and your analysis and your reports and your images and things like that. So the first part, so I'm going to go into the scripts complete folder. And the first thing that we looked at was the R basics practice. So this was Ye's part of it. So, and this was, again, just your very basic, you know, working directory. Here's how you input stuff into the console. And then how do you create objects and how do you assign values to the objects? And, you know, just some basic housekeeping, you know, how to import files. So this was one of they went through analyzing some calibration data, you know, looking at, you know, just some basic, you know, the structure, summary, how to work with data frames, you know, just kind of like the things that you would go through in a basic RStudio, a basic like R introduction, right? So, you know, working with plots. And again, we specifically kept this very simple. Like, we did not talk about packages. We didn't, you know, I don't even think we said the word package. I think the only one that we might have mentioned, was knitter, just in terms of the R Markdown. But for the analysis portion, we kept it, you know, very, very simple. We talked about how to export and make a plot. So all the things that you would normally do in your data analysis workflow. So that was Ye's part. And we did try to use either R script files or R Markdown files and have the students work there. Ye did have some slides in there. They're in that main directory, just as an introduction. But I found it that, you know, while teaching, for me at least, it's kind of difficult to, you know, kind of have more than one window open. So like if I have slides going on over here, and then I've got, you know, my note file that I'm taking here, and then I have the file that I'm working on here, and then, you know, trying to find, you know, it was just too much. So I've become a big fan of either using scripts or Markdown documents and just having the students work completely within that one document. And for some of the lessons that I've done at Caltech, those have worked really well. So that was Ye's part of it. And we'll go through Steve's part of it here. So QSAR models, so basically quantitative structure activity models are basically like, you look at a chemical structure and you look at a property of that chemical and you say, okay, well, if I change the structure of this molecule in these ways, how does that affect this measured property, right? So in this case, Steve has a set of data looking at a series of compounds that, you know, have incremental changes in their structure, and it says, well, how does that affect the acidity? How does that affect the pKa? So he goes through importing the data set and then reading the data in there. In the interest of time, I guess I'm not going to go through the actual things, but again, the files are here and the link is in the slides. So you can go through and run this experiment yourself. And then he goes into just very basic modeling. It's like, let's just do, let's use the LM function and, you know, create a model based on this data saying, okay, what's the, you know, relationship between the pKa and the sigma m variable based on the benzoate data. And then he goes through and you know, you make a plot, you take a look at it, you can put a fitted line in there, you know, print out the summary, and all of that. And we do this a couple of times, you know, looking at, you know, the data, you know, again, some basic R commands in here. I mean, and again, this was kind of adapted from an undergraduate lab. And then going about building the model. So then, and I don't think we got through all of this. And again, something else I'll talk about. So we go about the building the models, and the idea is that you use the data to look at a bunch of different parameters and say, okay, which parameters are the most closely affected by, you know, or most closely affect your measured property. So this is a really great example if you're going to be teaching something like this, because you're doing the same thing over and over again, right? You're running the same functions, you're just changing a couple of variables. you know, and in education, you know, as you're repeating things, you know, things start to stick and they start to make sense. So that's the other reason why we thought this was just a great model to use. So then, and then of course, you know, there's a couple of iterations of looking through, okay, well, which, you know, descriptors are the best, et cetera, et cetera. And then what does it all mean at the end? And, you know, we had enough people with enough chemistry background in there. I think we had a very small discussion about that. So, but the idea is, again, finally, the last part that I'm going to look at is, okay, so we have all this data. So what do we do with it, right? So then here comes, so the part that I talked about was putting this all together and saying, okay, let's write our lab report, right, in Markdown. And, you know, one thing that I mentioned and a lot of students, you know, immediately squealed in pain. I said, you know, have you ever tried to insert something into a Word document and then your formatting gets screwed up? You know, has Excel screwed up, you know, your date variables and this, that, and everybody was just like, yes, horrible. I said, those days are over. Gone are the days of, okay, well, I need a Word document to give to somebody, but my date is in Excel, and then I need to make a PowerPoint to give to my group meeting. No, we're done with that. So it's like write once, publish to many, and that was actually very, very popular. So the basic version that the students saw of this version's a little bit more filled out, was we talked about, okay, how do you put data into an R Markdown document? You know, here's the introduction, and, you know, we gave them some of this stuff. And then I had them do a little bit of formatting. So for example, I'm going to skip down just a little bit. So like, for example, there were parts in there that say heading 3, and it's like, okay, if you want to put a 3rd level heading and, you know, you want to add 3 hashes, or if you want to make something bold or something like very basic stuff. But then when we showed them, it's like, okay, you know, you don't have to, you know, copy and paste an image. You can actually get, you know, you can link your actual data into the report. And everybody just absolutely adored that. That was that went over very well. And then I showed them, we did very elementary in putting in citations. I think there was one, apologies for the fast scrolling. There was one there. So for example, we had an example bibliography file. We showed them how to put citations in. And this was extremely popular. And then we showed them, you know, you can knit to, in this case, this would go to PDF or Word, but then you can change it up in your in your YAML and say, okay, well, I want this to go to slides, or I want this to go to, you know, a notebook or whatever. And this went, you know, we got really, really, really good feedback on that. Okay, so I've got a couple minutes left. Go back to my slides briefly. So overall, we thought it went really well. I think a lot of people liked it. They got things out of it. Everybody wanted it longer, and we knew this was coming. Or, you know, from our perspective, you know, we might be able to make things a little more, you know, choose content a little more judiciously. And, you know, we weren't super strict about enforcing our breaks, which we should have been. But there were a lot of people who said they would come early, you know, and pay the expenses to come an extra day if we did like a longer workshop, you know, for, you know, a reasonable price. So we felt really good about that. A lot of people asked for print handouts to follow during the lesson. So as you saw, a lot of the files we used were very heavily marked with comments. But very valid feedback was that, okay, well, what happens when that gets scrolled off? You know, people might lose their place. And so printout would have been easier to follow. And usually in carpentry workshops, we do give handouts with at least like commands and things like that. So that's something we'll look to improve. And we did get some comments. We had an issue with the low color contrast on the monitor. So for our studio, the comments appeared as green. And we didn't have a high definition display in the room. So that was a problem, which, you know, there was next to nothing we could do about that, but it's something that, you know, going forward, you know, we'll have to be a little more judicious in terms of taking a look at our, you know, our setup and be cognizant of that. So, all right. So that's, I think I've got 5 or 6 minutes left for questions, but I did want to thank you all for your attention. I have to acknowledge ACS Pubs. Without them, we wouldn't have been able to pull this off, and also with the Division of Chemical Information, y'all. And I want to thank Yiwei, because I finally had a good excuse to sit down and learn Thuringian properly. So yeah, so with that, we got a couple of minutes, and I'll take any questions that anybody might have. And I'll go back to front, so if you want to grab the URL.
Lambda has a question.
Sure, ask away.
I will just repeat it. What do you think of Google Colab? I have written a few R bioinformatics tutorial. It's quite often a pain to install package, and it doesn't have RStudio shortcuts. But the nice part is they give you like 12 gigabytes of RAM and about 100 gigabytes of disk space.
To run your processes.
Google Colab.
So I haven't played with that, but I'm interested in that. And actually, thanks for bringing that up. Now, we did have somebody who kept saying that RStudio Cloud kept crashing, but this person was doing not course-related stuff. I don't know what they were doing. All right, they were doing like their own thing. I don't even know what they were doing in the class, but they were whining that RStudio kept crashing. In the class, though, nobody had any problems with it. So, I guess as long as, RStudio, as long as they keep that cloud infrastructure beefed up, I would say that would be my first choice. But I'm open to fooling around with Google Colab. I just haven't gotten a chance to yet.
I've used it before. I'm not sure how to have the R session running it. I had notebooks, Python notebooks.
Yeah, actually I know how to get the R session. So basically, so if you already have Anaconda installed on your computer, you create an R kernel and then type in some R code in it, like library tidyverse, and then even if it's just one line of R code, and then you upload that to Google Colab, and then it will start an R session.
Oh wow, that sounds pretty simple actually.
The nice thing about RStudio Cloud is you actually get the RStudio.
Yeah, yeah, I like that part. It's just that they said they only have like 1 gigabyte of RAM.
Yeah, and for what we were doing, that was way more.
That was fine.
That was more than enough. But yeah, if we were going to do something more involved, in terms of modeling or graphics, then yeah, I could absolutely see that being an issue. And maybe RStudio, maybe going forward, they'll beef the cloud up, which I think would be a great, that would be great.
Yeah, hopefully they do.
Yeah, but no, good question. I'll check out Google Colab.
Any other questions? Do you have to predefine what packages you need in RStudio Cloud, or do they have everything on the CRAN?
Yeah, well, when you're defining the environment, when you're setting it up, you can specify what packages to have loaded in the environment, and they have a large. I think you can install them. I think even from CRAN or from GitHub. And it'll just load it into the environment. And then when the environment deploys, everybody who's logged into that environment has access to it. Like to my knowledge, I don't think that there's a limited number of, there's a limited library of packages to pick from. I think you can install, almost whatever you want. Again, within the limits of, the memory and the computing environment.
Yeah, Kai has a question. I think it's about what we just talked. Persistent environment in RStudio Cloud.
Yes. And so you can specify the version of R, you can specify packages, you can specify what's installed, what's loaded. Yes, absolutely.
I have 1 minute. Is RStudio Cloud expensive?
It's free.
If you want to get more power, do you have to pay? Actually, don't know.
I don't know. I don't think that there's a paid version of it yet because it's still technically in alpha or beta. But I wouldn't be surprised if that's something that because we reached out to them and we said, hey, we want to do this thing. And they were fine with it. They said, yeah, more power to you. Let us know how it goes. Because I think they're still doing a lot of testing and development. But for now, as far as I know and I've heard, it is free. It is going to be free. But I wouldn't be surprised if they start introducing pricing, like a pricing tier based on computing power available. So
how many storage do we have from the RStudio Cloud?
How much storage?
Yeah, like the memory.
Well, like Lambda said, for running stuff, I think you get a gig.
Oh,
Well, disk space.
That's a good question. I'm not sure. I think it's a fair bit. And a lot of and of course, I mean, for this project, we didn't even think about it because we had like some scripts and some markdown files and like one picture and some slides, so it was like minimal. So we didn't even worry about it. There's probably a limit. It's probably higher than I would need, but.
Okay. Thank you.
Thank
All
you,
right.
Donna.
Yeah, so I realized that I didn't have my contact info anywhere on there. Yeah, just Google me, just Donna Wrublewski, Caltech, and you'll find my info. It's dtwrub@caltech.edu. So, all right.
I can send them in the chat box. So
There we go.
oh, cool.
All right, I will stop sharing my screen and hand it over. Thank you all so much.
So am I the next one?
Yeah.
Okay. Let's share my screen. Yeah, so can you guys see my slides?
Yeah.
Okay, first screen. So today I want to talk about how to draw fractals from root finding iteration in R. It's a little like class project that I did this semester. I feel it's quite a fun project because we are all like stuck at home, have nothing to do. Maybe we can draw some fractals to have fun. Okay, so today I want to first introduce the concept of root finding and what a root finding algorithm is. Then I will go over these two most common root finding methods. So they are Newton's method and secant method. And after that, I'm going to draw a connection between like root finding algorithms and how to draw fractals. In the end, if we have time, we can get started, create some like our own fractals together. So I just want to make sure, like, have any of you heard about root finding algorithm or like Newton's method before? Cool, cool, it's nice. Yeah, maybe I can go over it. Let's see. Yeah, let me know if you have questions. You can just unmute yourself or like type into the chat box. Okay, so the first, I want to introduce the concepts of root finding algorithm. Basically, a root finding algorithm is a type of algorithm that can help us find the values that can make a continuous function equals 0. So for example, here we have a function curve, and it crosses the horizontal line of 0 at 2 places. They are when x equals 1 and when x equals 7. So here we call 1 and 7 roots of this continuous function. So like generally speaking, if we have a value of a which can make fx equals 0, we call a the root of this continuous function. So however, we cannot use root finding algorithm to find the exact value of a. We can only find the approximation to the a. So you may be wondering like when we can apply this root finding algorithm. For example, if we have an equation here, fx equals gx, and we want to solve this equation, we can first make a transformation to let hx equals fx minus gx equals 0. And then the equation solving problem becomes a root finding problem. So we can use root finding algorithms to solve any equations from two continuous functions. And root finding algorithms requires one or more initial guesses of the roots. And we also need to set up a maximum number of iterations. And the algorithm converges when it finds a sufficiently accurate guess of the roots within the maximum number of iterations. Otherwise, it fails to converge or it fails to find a root. So that's why like root finding algorithms cannot like always find all the roots from the function, because we need to set up a maximum number of iterations to allow the function to run before conversion. And it also depends on how far away the initial guess is from the actual value of the roots. Okay, so there are a list of very famous root finding algorithms out there. I think the most famous one is called Newton's method, which is also known as Newton-Raphson method. So here in this graph, for example, if we want to use Newton's method, we have to first provide an initial guess, which is maybe x0 here, the initial guess of the root A. We call this x0. And then we find a tangent line here for this function at the value x0. So then we can get this equation. The derivative of the function at x0 equals the slope of the tangent line, right? And then we can see the tangent line across the horizontal line of 0 at maybe x1, we call it x1. And then we can plug in y equals 0 and x equals x1 to this tangent line function, because x1 is on this tangent line. Then we did little transformations. We can get a function to represent x1. So x1 here is our next best guess to the roots. So x0 is our current guess or the initial guess of the roots. So we can keep going or keep repeating this process, get the next best guess, which is x2. So here's a little gem or a little GIF to show the process of Newton's method. So here first we find an initial guess x1 and draw a tangent line here to get the next guess x2, and then a tangent line x3, x4. So we can see these x's are approaching the roots, and x1 is very close to the root right now, or x5. Okay. Then we get our general function for the Newton's method, which is the next best guess equals the current best guess minus the value of the function at the current best guess divided by the derivative of the function at the current best guess. And here are some computational examples, finally some R codes. If, for example, if we want to find roots for the function x to the power of 3 minus 1, we can first create a function for this function. So this function is returning a vector with 2 elements. The first element is the function itself, and the second element is the derivative of this function. Okay. Then we can create a Newton-Raphson function, which takes about 4 arguments. The first argument is the function that we just created. We can put this function to the first argument, which is a function for which we want to find out the roots. And the second argument is the initial guess that we just give to the function. And the third one is a tolerance, which means how accurate we expect the final guess to be. So here is 9-digit accuracy. And the last one is the maximum number of iterations that we allow the loop to run before conversion. Okay, so the next method is called secant method. The difference between secant method and Newton's method is that Newton's method is taking on a tangent line function. So it's why we have to provide a derivative of the function to the Newton's method. However, for secant method, it's using a secant line to find out the next best guess. So it's why we have to provide 2 initial guesses for a secant method. But we don't have to provide a derivative for a secant method, which is good because we're not always know the derivative of functions. For example, in this graph, we can, if we provide 2 initial guesses, x0 and x1, and we are assuming x0 is the older guess, then we draw a tangent line for this function curve across x0 and x1. And this secant line, and this secant line across there's the horizontal line of 0 at x2. So here x2 is our next best guess. So we can use x2 to replace x0. So now we have 2 best guesses, x1 and x2. So similarly, we can repeat the process to draw a secant line across x1 and x2 to find our like next best guess, which is x3. So this function is showing the slope of the secant line across this x0 and x1, which are our like two initial guesses. Because x2 is only secant line, so we can plug in y equals 0, x equals x2. And then we can do a transformation to get a function to represent x2. And we can repeat this process until we get a sufficiently accurate best guess. Here is the general format for the secant method. Okay, some computational examples. For a secant method, it takes 5 arguments because it needs 2 initial guesses. So we have x0 and x1 here. And similarly, this one is a function for which we want to find roots. And this one is the tolerance or the accuracy that we desire for the final guess. And this one is maximum number of iterations. So because secant method is taking 2 initial guesses, it's always running much slower compared to the Newton's method. Okay, so right now you may wonder like how to draw fractals by using these root finding algorithms. So first, root finding functions can also be applied to find roots for complex functions, which are functions for complex numbers. Just to refresh your memory, a complex number always has 2 parts, like real parts and imaginary parts. And complex numbers are always on a complex plane. Each root has a basin of attraction in the complex plane, which is a set of all initial guesses that can cause the method to converge to that particular root. And these initial guesses can be mapped into images. And the boundaries of the basins of attractions are called fractals. This may sound like complicated, but basically fractals are those objects that with similar patterns on all the scales. For example, here is a GIF for the zoom in of the Mandelbrot plot. So we can keep seeing like similar patterns when we zoom in. Here is the Mandelbrot. And we have several famous fractals out there. The first, I think the most famous one is the Julia set. And the second one is Mandelbrot sets. So we have already seen the zoom in GIF from here. So if we zoom in enough, we can see a Julia set inside a Mandelbrot set. Let's see. This one is the Mandelbrot. So here we can see a Julia set. Yeah. And the third one is called burning ship fractals, which is quite not as famous as the first two. So you may wonder why it's called burning ship. If we wait until the end of the GIF, we can see a pattern showing a burning ship. Yeah, here we go, a pattern of burning ship. Okay, so the last one is Newton's fractal. Sorry, I don't have a zoom in GIF for you, but we can guess from this pattern. This one should be generated by the function for the x to the power of 3 minus 1, because here we can see about 3 roots here. And I guess this one should be the x equals 1. And I have a zoom in video with crazy music to show you the Newton fractals. Let's see if I can show it here. Can you guys see my video? Oh, cool. So can you guys hear the sound? The music? No? Let me try.
I think you're in the ad right now. Is that right?
Yeah, I'm seeing the ad too.
How about now? Music?
Yeah.
Okay.
Mhm.
So here we can see a Mandelbrot here inside a Newton's fractal. Okay, a similar one. Okay, so we'll see it again. If we zoom in enough, we can keep seeing the same patterns. Okay, let's go back to my slides. Oh, where's my slides? No, let me check. Okay, so far we have talked about the concepts of root finding and what root finding algorithms is and how to apply these root finding algorithms. And we also learned different root finding methods such as Newton's method and secant method. And we also know that we can draw fractals by applying these methods to complex numbers. Okay, now we can get started to create our new fractals. Before we go to draw fractals, I have some recommended readings for you. The first one is Introduction to Scientific Programming and Simulation Using R. I remember in like chapter 8 or 7, it describes some details about different root finding algorithms and how to apply them and different functions. And the second one is Newton Fractal Wiki page, which shows a lot of beautiful examples from Newton's methods. And this book is quite interesting. This one is showing a tons of examples of using other like math equations to draw beautiful graphs. And now we can head into my repo. Yeah, maybe I can send this link to the chat box so you guys can go to the repo to see some sample codes. Chat box. Okay, I just sent the link to the chat box. Yeah, maybe I can give you guys maybe 5 to 10 minutes to use the sample codes here to create your own fractals. So if you find out some beautiful fractals, you just create it, you can open an issue here. You see here, we can create a new issue and paste your graph here. So after maybe 5 minutes, we can see like what everyone's gets. Okay. So while you are working on that, I can just quickly walk you through my sample codes and some examples. So here I have some recommended color palettes. The first one is created by Emil, who is also like one of our co-organizers of the Meetup. He has a package for different color palettes. And the second one is the one that I really liked from Wes Anderson. Before you run the codes, please load these libraries first. And you can also go to this R Markdown file to just find the source codes for this MD file. So here is a function for Newton Rapham, which I just showed in the slides. And here, for example, if we want to create a graph for x to the power of 3 minus 1, first we want to create a function for that function and returns two elements. The first one is a function, the second one is a derivative. And this chunk of code is showing how we can create complex numbers. So x is the real part of the complex number, which ranges from -1 to 1. And here we are sampling 500 real parts from this window. And y is the imaginary part of this complex number. So we have 500 real parts and 500 imaginary parts. And then we create a complex number from these two parts, from like all the combinations we have, which is about a total of 250,000 complex numbers here. But you can see we still like didn't get a very clear picture, because if you want to increase the resolution of this graph, you may want to increase the number here, maybe to 1,000 or something. But like, please like do not increase number today because it will run very like slow. And here is the code to apply Newton-Raphson function. Here we set the number of accuracy as 9 digits. And here is the number, max number of iterations, 40. And we use geom raster to create a graph. And we use here argument interpolate equals true to make to smooth our graph. And you can put different color palettes here. So here is my trying like different types of color palettes. And here we zoom out a bit, which means we sample 500 real parts from the window, a much larger window from -10 to 10. Here we can see like very similar patterns in these yellow-white chains. And we should notice that like this color palette is doing very different thing, because this palette has a way more categories compared to this one, and has very different color categories. So that's why this palette is showing very different patterns compared to this one. So we can see the roots here, 3 roots. So if we zoom in enough, we shrink the window to -0.01 to 0.01. We can find out that there are a lot of initial guesses in the center of the graph that fail to converge. So that's why they show like gray color. And we can also change the number, like change the color for the null value. So can make your background much beautiful. Maybe we can set it as like black or white. If we move a bit to the left, we can take a closer look to the chains. Zoom in a bit. Also some like null values. Then we can also draw some graphs for x to the power of 5 minus 1. So here we can see there are maybe 5 roots here. And also in the center of the graph, there are some points didn't converge. I think this one looks quite scary. I don't know why. Maybe because of the color. And here is x to the power of 3 minus another x. The interesting of this one is that when we zoom in, we can see a Julia set here. So here we can see a Julia set, which is the most simple Julia set. If we zoom in enough, we can see there are other Julia sets on the edge of this large one. And we can also see there are some different number of iterations on the edge of this Julia set. So if we change a color palette, we can see more clearly the pattern of the iterations. So here are some graphs for exponential function. I really like this one. Okay, I feel like this one looks crazy. Too much roots here. This one is x to the power of 8. Looks chaotic. And the strange thing is that if we draw some graphs for sin x minus 1, we can see a similar pattern compared to the graphs from the exponential function. I don't know why these two functions have this kind of connection. Here, we can see a pattern on the horizontal scale. And this one is kind of similar, but it's vertical. And this one is for sin x minus 1, and that one is from the exponential function.
Neil just said something.
Oh. Is that in the chat box?
Yeah, he said well, Fourier.
Fourier. Okay, so this one is a secant method function, which is running like really, really slow. So you don't want to try today. Okay, I think we have enough.
Yeah, any questions?
With enough time, let's go to the issue. So anyone like upload any graphs yet? Oh, no, okay. Okay. Yeah, can you stop share?
Karen, where were we supposed to share our?
Oh, if we have some graphs, please like open the issue for this.
Open an issue. Okay.
Yeah.
I think people probably didn't have enough time to make the graph.
Yeah, I think so.
Yeah, I'm still playing around with it, but I'll definitely
please
put some
feel
stuff
free
up
to
there.
play.
This is so cool.
Yeah, so any questions before we passing on to Luke? The relation between complex numbers and fractals. Oh, it's a difficult one. Actually, I couldn't like understand enough about the complex numbers and fractals. I would know that if we have like complex numbers, you can create the patterns on the complex plane. But if you have real numbers, you may not see this kind of patterns.
I don't know why lambda said RCPP. Anyway, if you
so anyone have any like suggestion to speed up my code, I would really appreciate that.
Yeah, I just said RCPP.
Yeah, I think so. RCPP may be a good idea. Yeah. Okay, cool. It's 7:30 now.
Luke, are you ready to share?
Yeah, you want me to jump right in?
Yeah.
All right, I will remember how this works. Hey, those are my slides. All right. So now that everybody else did really like smart things, now comes the jock stuff. So basically, I'm a giant college basketball nerd, and this is my favorite R package called NCAA Hoop R, and it is pretty much the way that I learned to master R to the point where I could actually get a data analyst job at Cedars-Sinai. So I kind of want to run people through it. And we're going to figure out how I go to next slide in Google. All right, here we go. A lot of you, I mean, there's inevitably going to be people here who are not sports fans. And I know you're probably thinking, ugh, sports ball, really? But I promise you that there is something for everything here, or something for everyone here. One of the visualizations that I'm going to show you actually uses the PageRank algorithm in a really genius way. And just all of the viz here is really smart. And like I said, this is what I use to teach myself R, so that's why I'm passionate about this project. So before we get into it, this is me. I was born and bred in Kansas, and that's why I'm a giant college basketball nerd, because Kansas is a college basketball powerhouse. Before I got into analytics, I was actually working in journalism, and my last few years I had been working with content analytics. And so I thought once I got my master's degree that that's what I was going to go into until the opportunity at Cedars opened up. And here I am now after getting a business analytics master's degree. And I think a year and a half ago, I didn't know any R, so it's still crazy to me that I'm presenting something. So this is NCAA Hoop R. It was created by Luke Benz, who was at the time the Yale Sports Analytics Student Group's president. And basically what it does is it serves college basketball fans in ways that we see a lot of NBA fans being served with analytics for their sport all the time, but the NCAA hasn't been as quick to pick up on open sharing of all of that. So basically what this package does is go through all of ESPN's box scores and rips them and turns them into a data set that you can go and play with. But like I said, this has been a major part of my R journey. It's how I, found my passion for R. It's how I learned how to read the documentation so I could actually use the tools in here. And I mean, it was so engaging. I've actually managed to make a few contributions to the package. And I mean, I'm so dedicated to it that I learned how to do that as well, because I did not know GitHub before I started either. And sorry if you hear my dog whining at the door. She would like to play, but I'm a little busy. So a lot of the fun things that you can do with NCAA Hoop R start with scraping your team's games. And there's two ways you can do this, and I've got examples of both right here. The top one shows you how to grab a team's entire season. By default, if you don't include anything in that season call, it will give you the most recent season. So it would give you right now 2019-20, which ended short. Wah, wah. But yeah, you can basically do this with two calls. And what you see down here with the second example, the get PBP and season, and then a vector of games, the numbers that you have in the vector are just the end of a an ESPN URL for a box score. And luckily there is a there's a function in here, the get PBP actually, where if you go and, or actually no, it's called get game ID, where you can go in there and it will grab all of those for all of the game IDs that you need for the season for you. So then you can start analyzing your season right away. And once you do a get play-by-play or a get PBP call, this is what it looks like. These are all of the categories that you get at once. So a lot of things you can do, like, for example, one of the things I like to do is I will go in here and I will just play around with dplyr, and I will get only Kansas shots, so shot team Kansas, and not, yeah. And I would get plays that, have a shot outcome, a non-NA shot outcome, and that are false for free throw. And from there, I'll look at a lot of the different shots that happened, or I'll look at ones that have an assist on the shot and be like, okay, well, this is who's passing to who. But here's where it gets really fun. There's a lot of awesome plotting that goes on in this package. The first one is win probability, which you can see on pretty much any sports site these days, but I think it's cool that you can now just cook your own up. And this is like within a minute or two of the game being over, you can go ahead and pull this together and set that up. And you get to choose your color for the home team and the away team. So one of the things that we have in here is a database that tells you, what is which team's colors, which is one of the things that I contributed on. And so I'm able to put this to win probability together with just, three elements. It's game ID, the color I want for the home team, and the color I want for the away team. And we have another similar, actually, it's actually been part of a meme, the win probability chart. And this was a game, I believe, that Nevada was up like in the high 20s or maybe even by 30. Or wait, no, it was Cincinnati was up in the high 20s or somewhere around 30. And then Nevada came back, and that's why you see that happen where they cross in the win probability. But here's just all the jokes that somebody did with it. The next one we have is just kind of tracking how the scoring went throughout the game. So it's just a step of the score as it went along. But again, it's one of those, 3 commands in here and you've got it. This is the one that I really have a lot of fun with. The assist networks kind of show you how the ball flowed between players on shots where one player was credited with an assist and the other one was credited with a shot. So basically, what you can see here is when there is a wider line, that tells you that connection is more frequent between those two, from one player to the other, and that would be the direction of the arrow. So the boldest line we see here is from Brad Green to Evan Leonard. Unfortunately, the numbers for all these different lines aren't, quite where you'd want them to be, but you can see the 3 applies to the connection between those two. And this is where all the PageRank connections come in. Like you see hub score, auth score. I'm trying to run quickly right now, so I don't remember which one relates to basically your top assister and which one relates to your top scorer from assists, but it's all in there, and you can basically look at any game that you want from, I think, back to 2008 now.
Someone asked what was used for network visualization.
The great use for me is just seeing who.
No, I mean what package? I think.
This is all inside of NCAA HoopR.
What package did you import to draw this graph?
I think it's part of whatever's required with NCAA HoopR. I can't remember for sure, but I mean it has a bunch of requires that it comes with, so that's how I do it. Sorry, I don't know off the top of my head. And this is basically that same type of assist network showed in with the help of Circle Eyes. I know that's part of this now. But what you see on the left is really, really, really busy, but it shows you every player and all the connections, but it gets really hard to see. So I like to highlight a specific player like I did on the right, and you get a better idea of the lines that are going out are who they are passing to. And so once again, the thicker the channel that you see there, the more often that connection happens. One thing I'd really like to see in future editions is that you can see toward the end of his little sliver of the outside of the circle that some of them are not highlighted. Those are the ones where he was the one who was passed to. And it would be nice if we could like reverse the highlighting on this and be like, okay, well, here's all the different connections to him. So hopefully that's coming in a future version. One of the other things that you see in here is shot charts, and that's literally you have to type in just the game ID and you get shot charts back. unfortunately, this only works right now for teams that are like, Pac-12, Big 12, all the big conferences, because those are the only ones that ESPN tracks X and Y for. But, hopefully, as basically in sports, spatial is becoming the next big frontier in analysis. So hopefully a lot of that gets spread to the other mid-majors and everything else soon. And this is those shot charts, but just done as a heat map. You can also do season versions of this. And it's just one quick tweak from what we had on the other heat map. You just change this to heat map equals true. And these are examples where I've taken multiple games. And again, it's just a vector of, I've got 4 games here. And it gives you an idea of where all the shots are. It gets a little busy in the shot chart version when you do this, the non-heat map version, because it gets really hard to see what's a make and what's a miss. So that's when I really like to do the heat map. And one thing that really gets shown in here, I believe it's on the, yeah, so the one thing to compare is here we were looking at the Kansas shots on offense, and here in the heat map we're looking at the shots that were attempted against them. And one of the things that this really shows me is that we had a 7-foot center who was really good at stopping shots right at the basket. And so that's why you see a longer tail of where people were shooting inside, because they wanted to avoid him when they could. But what we're showing here is it's the exact same command. It's just you put, instead of team shot chart, you put op shot chart, and you get basically your opponent's shots. Here's some of the use cases, and I believe this is how it actually was birthed. Basically, Luke Benz had a project where he wanted to examine whether or not a coach taking a timeout had any effect on the game. If a lot of time coaches will call timeouts if the other team is on like a big run. And what he found is that it's actually possible to conclude that a timeout is worth about 1.5 to 2.2 points following the 5-minute interval after the timeout. Which, I mean, it's interesting that it takes that long for the effect, but I can also see that it makes sense. Just, it kind of opens up the opportunity a little bit more. One of the other big contributors that I see online is fifth factor plots. And a lot of this stuff gets really busy, but there's a lot that you can yank out of here. If you're looking for your specific team, then, I mean, you got to squint a little bit, but you're like, okay, well, I can, kind of get an idea of where they stand against other teams in the country. And on the right, what we see here is, one thing I'm really kind of pointing out is the little red and green that you see on the shot chart inside of it. Basically what he does is he maps all of the shots for every team in the nation, that's available. And then he calculates for each one of those little dots for that area, whether the team in question is shooting above the national average or below the national average at that area. So that's like really something that you can look back and be like, oh, well, we're better in the nation, in the high post if you're Auburn, or something like that. One person who does a lot of contributions and is able to pretty things up in Tableau as well is Matt Rain, who appears to be a big Dayton fan. And he's somebody I've ripped a lot of my ideas off of with permission. But you can see, like, pretty much a lot of people will rip the data out of this and just run with whatever idea they have. This is somebody who looked at individual shooting and different type of situations for the team for UConn. And I'm going to have all these slides available afterward. Here's something that I've done. I have my own season Shiny app that hopefully I can pull up here. We're going to pretend I know how to use this. The only thing is I'm going to have to like vamp for a moment because it takes a while to. Oops. Are you still seeing the slides or are you seeing the? I'm not sure what I'm sharing it. Sorry, what was that?
Slides right now.
Okay, let me. All right. Are you starting to see like at least the sidebar of a shiny dashboard?
Yeah.
Yeah, unfortunately it takes like a minute to load because what I really needed to do is Luke Benz went back and added a bunch of he's done a bunch of things on his repo where he went back and added all the games through the season, but I just haven't had time to go back and turn it into those static ones. Instead, this is going and ripping every Kansas game for the season directly off ESPN, and that's why it's taking forever. But I can show you some of the things that I add. Basically, you can check or uncheck any games that you want to analyze. One of the things that you can do in here is that you can add a weight for 3-pointers. So basically, if this says yes, then it counts them as 1.5, and if it's off, everything is just a 1. Minimum for player inclusion, basically, a player has to be on such and such a percentage of a team's assisted shots or assisted made shots in order to be included in the assist net. And so this would give me, they have to be at least 10%. And I also made, there's an option to where you can highlight the player and whether or not the shot charts are a heat map. And here's what it looks like. It's not the prettiest thing, but it was kind of my first tinkering with Shiny to this level. So I'm happy with it. And if I were to not select an individual player, it would show you that really rainbowy version again. But this is again where, especially seeing them on the same screen, you have the Kansas shots for and the Kansas shots against. You see the post presence of our 7-footer in the bottom one causing a little bit more havoc. And also the little purple you see in the arc in the bottom one shows you that the teams against Kansas were taking far more shots than Kansas was. All right, now we got to figure out how to get back to my slides. This has been Luke Knows How to Do Things. That's the share button. Oops. Okay, we see slides again. Oh, God. What is going on? All right, are we seeing slides again?
Yeah.
Okay, good. All right, so this kind of gives you an idea of one of the things that I've done just going back and ripping the data and looking around. This, I wanted to get an idea of, for, you know, every player, who are they passing to and where are they passing to for somebody who makes a shot off of one of their assists. So this is looking at basically every time that Devon Dotson passed the ball to somebody and the other person made a shot. So you kind of get an idea of who it's going to and where they're making it from. And I already told you that I'm one of the contributors to this package. I basically expanded the team color availability from 150 teams to 350 teams and added logos in if anybody wants to have any fun with GG image. We also, like I said, there are the season so far repos that Luke Benz has been putting together. All the mapping stuff that you see, including the shot charts and the heat maps, are done by Mayop and Sabaya and C. Ryan Campbell. Jared Andrews has helped basically put all the box score info that you see when you pull a get PBP. There's also a package if you ever want to look at, you know, how teams fare when somebody is subbed in and out, and that's called Big Ball R. I haven't done very much with it yet, but I've seen a lot of examples of people, kind of looking at, the optimal lineup for a team. And if you're a fan of women's basketball, Scott Nestler, I believe he teaches at Notre Dame, has put together basically a clone of this package called WNCAA Hoopar. And this is basically all the places that I look at when I'm nerding out on college basketball analytics. Luke Vins, who again was the creator of the package, has his own system of predictions and bracketology. And I believe a few years ago, he won a contest to predict just who all was going to be in the NCAA bracket. Ken Pomeroy is the golden standard for college basketball analytics. I believe he started off as a meteorologist, but he basically just does this full time now, I believe, and also writes for The Athletic. But it's $20 a year for access to his site. Bart Torvik is kind of a free version of Ken Pom, but it uses his previous version of his algorithm. Hoop Vision is somebody who does a lot of, this R visualization, as well as he used to be a film breakdown person. So you'll see him do a lot of stuff like, here's what an offense is doing, here's what a defense is doing, and he'll actually label it on the video. And it really just makes you feel smarter watching this. Starting with 2 seasons ago, the NCAA actually started its own attempt at data science with what's called a net ranking, but it's kind of been panned as something that still needs to do a little bit more learning before it's actually reliable. And that is all I have. I hope, even if you're not a sports person, that you enjoyed something out of this. And if you got questions, I've maybe got answers.
Any
Hey,
question?
Luke.
Hey,
How long did it take you to get up to speed?
on this package or just on R in general?
Oh, how about both?
I would say R in general, I was doing, before we learned that their CEO was a scumbag, I was doing data camp. And so I think I was going along pretty well with that. As far as this package, it took me a week or two to start learning how to read documentation to the point where I was understanding what I was doing and getting the things I want spit it out on the first try.
Any other questions? No? Thank you.